Welcome to This Explainer. Today, we're diving into something that completely flips our understanding of the universe upside down. For decades, astronomers just assumed that a solar system with two suns would be this chaotic, totally hostile place, like a cosmic blender, right? A place where planets just couldn't survive. But guess what? Recent state-of-the-art computer simulations have completely rewritten that script. We're going to explore the actual astrophysics of why dual-star systems might, surprisingly, be the absolute most efficient planet factories in the entire universe.
So here is the core question we are tackling today. It's a massive paradox. Think about it. If you've got two massive stars locked in this intense gravitational dance, their shifting poles really should just disrupt all the gas and dust around them, tearing apart any baby planet trying to form. Resolving this isn't just some niche trivia. It fundamentally reshapes how we understand planetary astronomy, and it completely changes where we're looking for new worlds.
Okay, real quick, here is our agenda. We'll start with the binary star paradox, move into binary systems and planet disks, break down the physics of orbital instability, define circumstellar versus circumbinary orbits, check out the disk fragmentation breakthrough, and wrap up with the scientific implications and final synthesis.
All right, let's jump right in. Section 1. The binary star paradox.
Astronomers actually call this the Tatooine problem. Because binary stars are so incredibly common in space, we honestly expect to see millions of planets orbiting them. But to date, we've only discovered a little over 50. The problem is that our telescope observations show a glaring absence. Traditional gravity models essentially say the environment is just way too violent for planets to coalesce. So we had this huge mismatch between what we expected and what we were seeing, meaning we were clearly missing a massive piece of the planet formation puzzle.
Moving on to Section 2. Binary systems and planet disks. So what exactly are we talking about here? Well, a binary star system is simply a system where two stars orbit a common center of mass. We usually drop them into two buckets: close binaries, where the stars are super tightly packed and whipping around each other, and wide binaries, where they are vastly separated, sometimes taking thousands of years to complete a single orbit. And the absolute most vital thing to understand here is that these systems are extremely common in our galaxy. A single star like our Sun is actually kind of an anomaly. Because binaries are the rule, not the exception, we have to understand them if we want to understand how planets form basically anywhere.
Now this is the crux of the problem. Normally, with a single star, planets form in a protoplanetary disk. It's a stable, flat pancake of gas and dust spinning smoothly around one solitary gravitational center. Dust clumps into rocks, rocks clump into cores, and boom, you get a planet. But when you add a second star to the mix, you get a completely different beast. You now have two massive gravitational centers relentlessly churning that gas disk. It's no longer stable, it's a chaotic gravitational battleground being yanked in conflicting directions.
Section 3. The physics of orbital instability.
Let's break down the actual cause and effect chain here. It starts with those two binary stars interacting in the center. As they orbit, their shifting masses create severe gravitational perturbations. Think of them as giant, invisible waves of gravity rippling outward. Step 3, those ripples completely disrupt the protoplanetary disk, violently stirring up all that gas and dust. So by step 4, the standard way planets form, which relies on gentle collisions and very gradual buildup, becomes practically impossible. And the end result, step 5, is that vastly fewer stable planets can ever hope to survive in those inner zones.
That chaotic inner region is appropriately known as the danger zone. The sheer mechanical violence of those competing poles makes it a totally hostile environment. The instability is literally so severe that if a young planet somehow starts forming there, the erratic gravity is probably going to eject it right out into deep space, smash it violently into another forming planet, or just prevent it from gathering enough material in the first place. No chance.
Part 4. Circumstellar versus circumbinary orbits.
Okay, so if you're a planet trying to survive this chaos, you strictly have to fit into one of two physical configurations. Case 1 is a circumstellar orbit. This is where a planet orbits just one of the stars. For that to actually be stable, you absolutely need a wide binary system, meaning that second star has to be super far away so it doesn't interfere. Case 2 is a circumbinary orbit, where the planet orbits both stars, kind of treating them as a single mass. The catch here is that it requires a close binary system, and the planet has to orbit way outside that central danger zone we just talked about. If a planet doesn't fall neatly into Case 1 or Case 2, it is not going to make it.
Section 5. The disk fragmentation breakthrough. Now, this is where things get really exciting.
State-of-the-art computer simulations led by Dr. Matthew Teasdale completely flipped the script on this. His models prove that, yeah, the inner orbits are definitely lethal, but if you just move farther out, the whole system transforms. What we thought was a universally dead zone actually turns out to be an ideal, wildly productive environment for creating huge planets.
The physics behind this is something called gravitational instability. Far away from those central stars, the gas disk is massive and very cold. Under those specific conditions, instead of dust slowly clumping together over millions of years, the disk literally breaks apart. It fragments under its own immense gravity. Researchers actually call this outer region a fairground. This fragmentation is incredibly fast and wildly efficient, rapidly churning out multiple massive gas giants that are often way larger than Jupiter.
So within a single star system, you end up with two completely mind-blowing extremes. Close in, you've got the forbidden zone, violently chaotic and a total dead end for planets. But out on the edges, you have the fairground, a massive, fragmenting disk rapidly mass-producing giant planets. In fact, these simulations suggest that because of this fragmentation, binary systems might actually be far better planet factories than single stars like ours. It's wild.
Finally, Section 6, Scientific Implications and Final Synthesis. So, why does all of this matter? Well, for starters, it completely rewrites the playbook for where our biggest telescopes, like ALMA, the James Webb Space Telescope, and the upcoming Extremely Large Telescope, are going to look. We now know that real-life Tatooines aren't nearly as rare as we thought, which is huge for habitability studies. Plus, it beautifully solves a lingering mystery, the origin of rogue planets. A lot of those free-floating worlds drifting out in the dark were probably born in the fairgrounds of a binary system, wandered just a bit too close to the forbidden zone, and got violently kicked out.
Let's bring this all together into a final synthesis. What do we know for sure? It is absolutely confirmed that binary stars are highly productive environments for gas giants, all thanks to the new insight of gravitational disk fragmentation. What's uncertain is exactly how many planets get ejected to become those rogue worlds. That's going to take future research with next-generation tech like the ELT. But perhaps the harshest truth we have to accept is that the inner region of these systems is a permanent, forbidden zone, where survival is just impossible.
I want to leave you with a really wild thought to ponder. If binary systems actually are the universe's most efficient planet factories, churning out gas giants left and right, how many of those massive worlds lost their footing? How many giant planets are currently drifting completely unseen through the cold dark of interstellar space right now? It's kind of spooky to think about. Thanks for hanging out for today's explainer on binary star dynamics, and as always, keep looking up.